Thank you very much for a very kind introduction. And I've been very delighted to back to Joseph Stephen Institute because this was part of my home 14 years ago, actually. It's almost 14th-year anniversary in this coming January. So it was I'm very happy to see my colleagues, my former professors, and the place that I used to work around here. So today I'm going to talk about STM, molecule manipulation. And as you already see in the logo, I put it IJS logo instead of normal logo with atomic manipulation. Just recently I saw in the web. This is just, last week I took in Japan. I was amazed with this conference dinner was prepared. It's part of the nanostructures, but this is not nano. Let me start with a few introduction. And I want to show first one of my earlier paper work in Joseph Stephen Institute. As you see, this was me. It was published in '96 with late Professor Marinkovic, Professor Prodan, and Professor Igor Mushevich. It was one of the earlier STM paper that I did work. Before I start my talk, I also want to introduce briefly the place that I come from. I think this is a little bit moving up. This part is missing. Maybe I will try next one more round. It's okay. I think we can work out in this way. All right. So this is just the map of the United States, and this is where the Ohio is located. I think many of you may already know. And this is where the Ohio University is located. So there are a few things I'd like to mention. Is that Ohio, we have the largest Slovene Americans. In North America, it's in Ohio, and here in the Cleveland area. So it's about over 60,000 Slovene Americans. It's also the most German Americans, 2.5 million. So every year, among my students, about 3 or 4 in my class, undergraduate class, are Slovene Americans. So I used to talk about Slovenia to them. And some of the images, this is some pictures about the university. And we are over 200 years old, so one of the oldest university for American standard. This is the physics department. And we have a very nice aviation engineering department, University Airport. And we can have a jet plane if we want to go to Washington for grant proposals. That's one of the very famous open-air theater for music because we have a very good music department as well. And that was last week, some of the pictures of Frozen. So it's very cold now. All right, so let me start my talk. Why atom molecule manipulation is important. Let me show with this graph. This was, I just took it from Merrill Lynch about the technological breakthroughs come at the year round. As you see, in 1771, the textile was started introduced. About 30 years later, it was just a boom. It stabilizes. It takes about 50 years. And then comes railroad, automobile, and computer technology. In 1939 was started introduced. 69, it was a boom. 2025, it will stabilize. Now we are the age of nanotechnology. As you see, started in 97, about 25 to 30 years is the introduction, and then this is the age where nanotechnology will be prospering. So it will create billions of wealth, and there are a lot of money has been already put in U.S. and many European countries, also in Japan, for nanotech. Now, if we are talking about the nanotechnology, we need to know another thing. That is the devices, the scale of the devices, electronic devices. This is the devices of the CMOS transistor, and this is the year, that's the size. And as you see here, and since 1970s, device sizes are gradually scaling down. And this is called Moore's law. And if we plot this scale, you will see that we hit to the bottom somewhere. And this arrow shows the 2007. This is current today. We are at the size of below the 65 nanometer today. And if we continue this graph, we will reach to the below 10 nanometer, the scale in 2020. It's not long. It's about 12 years from now. So if we want to build an industry, such devices, somebody has to be doing research today in order to find with the single atoms and single molecules, because that's the scale of individual atoms and molecules. So today my talk concerns with the how do we study at the atomic level and a single molecule level. How can we build the devices, for example, but more from the basic science point of view. And this map shows STM manipulations at current stage. Well, I already put it here, IGS, as the group of Professor Prodan has just recently succeeded to move the atoms. And there are not many people, but this is a high technology, basically, to control the atoms at atomic scale. As you see, there are only very few laboratories around the world, 3 in Europe, 3 in US, 1 in Canada, 1 in Japan. All right, so what is a scanning tunneling microscope? It was invented in 1980s, and these two gentlemen, they got Nobel Prize for their invention, Rohr and Binnick, for invention of the scanning tunneling microscope. In scanning tunneling microscope, we have a very sharp needle, so call it a tip. And that needle, this is the scanning electron microscope image of the sharp tip and the sample by the group of Edmonds from Zurich, Jülich. And this shows how the STM position the tip and the surface. And then what we do is that we apply the voltage between this sharp metallic tip and the surface. The distance between this is less than 1 nanometer. Actually, it's about 5 angstrom. And if you apply the voltage, then we scan the tip across the sample surface, and we get this kind of profile of the surface. Because STM has an atomically sharp tip, we can get the images of individual atoms, also the molecules. All right, so my group at Ohio University are doing the next level of using the scanning tunneling microscope. We are actually not just to take as the image tool, we are actually using as a manipulation tool, sometimes also as an engineering tool. So how do we manipulate the atoms and molecules with the scanning tunneling microscope? We can use the electric field between the tip and the sample, or we can use tunneling electrons injecting between the tip and the sample, or we can use the forces acting between the tip and the sample. For that, we have to approach the tip close to the atoms or molecules that we want to manipulate. There are 4 basic manipulation modes. The first one is known as a lateral manipulation. And in this case, we approach the tip close to the atoms, and we laterally move the tip across the surface. And the atoms or the molecule follows the tip in this continuous manner, as you see here, with some type of this kind of shapes. And this was first introduced by Don Eigler from IBM by writing the IBM logo. And this technique is not just to move the atoms around. We can also use, for example, this is a recent paper published by my former group, and I also have kind of a comment paper there. For example, rolling of molecular machine on the surface. This was in Nature Nanotechnology in 2007. We can not only move the atoms and molecule, but also we can actually induce the other functions like rolling or mechanical function, and we can detect this signal of the rolling, how a molecule is rolling, for example. In this case, the wheel, molecular wheel, these are the 2 wheels connected with the chain of the molecule on the surface. So this is now an emerging research field to build the molecular devices or mechanical devices by building using the single molecules. The second technique is known as the vertical manipulation, where we can transfer atoms and molecules between the tip and the sample. The third technique is an important technique known as inelastic tunneling. In this case, we inject the tunneling electrons to vibrate the molecules or to rotate the molecules or to break the molecules. We can actually take out individual atoms from the molecules with a single bond precision using this technique. And how do we control that? What we have to know is when we inject the tunneling electrons into the molecule, what happens is electron is temporarily captured in excited states and energy is transferred to the molecule, And we can control this transfer energy. And from this diagram, you can see here, we can excite by using the single electrons or multiple electrons, depending on the situation. And we know how many electrons are involved in energy transfer process from this equation. Transfer rate is proportional to the current to the power n. Here, n is the number of electrons involved. So please remember this equation, rate proportional to the current to the power n, because I will come back to this at a later point. Finally, the last technique is we can also weld the molecule fragments by injecting tunneling electrons. Now, the STM is not just a manipulation tool, it's also the spectroscopic tool. We can do, for example, IV tunneling spectroscopy. By changing the voltage, we can measure the current, or we can measure the DIDV, which is a first derivative signal that tells us electronic structure like density of states, or the second derivative signal that tells us vibrational signature of the molecule. And combined with this, all the manipulation techniques like lateral, vertical, IETS, and bond formation, we have a plenty of choice we can do to study the electronics, mechanical, physical, and structural properties of individual atoms and molecules, so that we can see whether this molecule will be fit to create a device that I'm going to show you with 4 recent examples from our group. All right, so this was some of the images from my group, my students building our home built the low temperature STM. Normally, okay, sorry, some of the images are cut off up. I'm sorry about that. And this is a low temperature STM in my group at Ohio University, and this is the inside how it works. And we have the Bisoka beetle type, and this design is based on my former group in Germany. It's a modified design, and similar design you can see here also in Professor Proden's group here. And of course, this is some of the locations. So vibration is one of the very important point of view, that if we want to move the atoms and molecules, we need to have absolutely quiet environment. So in my case, I have a separate building, separate location for the lab, and this is some of the images of my lab instruments at Ohio University. So we work at the very low temperature environment and very ultra high vacuum, around temperature negative 11 torr. We are working at a low temperature, about 4.2 Kelvin, and we work in a very low drift environment. The drift is about 0.1, which is 1 angstrom per hour. With drift means you position the tip and they are staying the same place. It literally shifted, it's a drift. And of course, we have a long time working condition. We work in the same sample area for sometimes for 6 weeks, 3 weeks to 6 weeks. And we are mainly working on metallic samples because it's easy to prepare and easy to work with. And molecules I'm going to talk about are deposited by using the home-built Knudsen cells, or recently we are also putting by means of pulse injection technique. All right, so I'm going to give you a few examples before I'm going to the final results and the key subject of today. And this is an example of the chemical reaction that we realized. This is my old work. This is not mine, I'm sorry. This is the original work published in 1904, 100 years ago, called Ullmann reaction, where we put the copper powder into iodobenzene liquid and heat it up, and then we have this chemical reaction. Iodobenzene plus copper, it results in a biphenyl, this molecule, plus copper iodide. So I'm going to show you how do we generate this. Actually, I'm having a little trouble with these slides because some of them are up there, not here. Anyway, we started with the iodobenzene molecule up here. It's not in these slides. And then we injected electrons to break the iodine. And afterward, we pick it up, the iodine atom, with the tip here. It's gone. This one is remaining. And then we move the remaining benzene ring close to each other. Finally, here we inject the tunneling electrons and join this guy and move it to check the stability and put the iodine atom back. I will show you with a small cartoon here. We inject the electrons to break the iodobenzene, pick it up the iodine atom with the tip, and move this benzene ring close to one another. This is actually how the tip is moving during the process. Inject the electrons to weld the benzene rings, and then move entire molecule to test how stable it is and put the atoms back here. So this is, we call it as engineering of single molecule. We can synthesize one molecule at a time. We can test the chemical reactions to see how it works and to understand at the atomic scale. This is just a demonstration. This was the old work published in the 2000 in PRL before I moved to Ohio University. Another example is just for fun. So this is now how I see it. We are actually reaching to the surface at the atomic scale. So this is how I see it. Instead of STM tip, we can actually go and touch the atoms, pick up the atoms. We can listen the sound. We can move the atoms. We can create nanostructures to study the special effect. Okay, so this was one of the examples before I move on. And I want to explain another thing is the surface states are standing waves. So one of the important properties of metallic substrate is there is a two-dimensional electron gas on the surface. In this case, one of my colleagues in Berlin has written this Q. Q is here is a quantum individual atoms on copper 111 surface, and the atoms are also copper. As you would notice, inside there is a wave-like patterns. This is caused by the electrons scattered from these atoms, because electrons has a wave properties, so that you see this kind of a standing wave patterns, and the wavelength is exactly half of the Fermi wavelength. And this is important part of my talk, because we can engineer these electronic waves for our applications. And now let us go and look a little bit closer in the 3 dimension. So these are the atoms, and this is the wave, atomic electronic wave, and this is how you will see it. These are the real STM image we render in a 3 dimension. So these are the electron waves which will play important roles, and we can engineer simply by locking with the different structure by putting the atoms. And you will notice in IJS logo, the recent logo, and also there are water-like things near the atoms. All right, so I will start my real part of the talk. I'm going to give 4 different examples, which is the first one is the atom manipulation. And the second part is the molecular wires, where I'm going to talk about the single molecule gun. And the third part is the magnetic molecules, where I'm going to talk about the single molecule switch. We call it the corner switch. And the final part is the nanoscale biomolecules, where I'm going to talk about the chlorophyll single molecule switch. So let me start with the atom manipulation. So this is just the concept of the atom manipulation. This is this human scale. I just take it from the internet, from the Paris. When we build the structures, buildings and bridges and our scale, we create the materials from the earth and we build the structures. Similarly, we can build the structures by taking out the individual atoms from the surface, and we can build the structures, different various structures. Now, to do that, we have to have atomic scale control. So that comes in important physics. How do we create the atoms? We can deposit the atoms on the surface, but we can also take it out from the materials, because we are working on the surface which is made of the atoms. So it comes in with the important physics. There are 2 techniques to take out the atoms. The first one is by using the brute force, just by crashing the tip to the sample. If we apply the correct voltage and if we crash it, what we will find is this is the crash site, for example. And far away from the crash site, you will see that individual atoms are scattered. Close to the crash site, you will see this kind of a big clusters. And these atoms here, I show here, are reorganized to build the structure. For example, in this case, we draw the 2 lines. Here is a 3-dimensional image of these 2 lines. And these are the individual atoms, and what we see here are electronics waves between the 2 atoms, 2 lines of atoms. And this is the proof that these atoms are substrate atoms. We fill it back to a small hole, and as you see, after filling, the hole is completely gone. You see nothing. It's not distinguishable from the neighboring area. So this happens only if the atoms are the same material as the substrate. For example, in this case, this is the silver 111, so these atoms are silver. If we use other types of atoms like tungsten or copper, we will see here changes, because electronic structure is not the same. The second technique is we just published in PRL and did this year, is by using the tip cluster interactions that we can produce individual atoms. To do that, first we deposit a small cluster on the surface, and then we choose the protruding part. I'm sorry that the colors is not correctly representing, something is wrong with my computer. And we approach the tip close to the protruding part, and we push it down the tip. We can get one atoms coming out, and the height drops down here. And we can explain this with the theory calculations where my collaborators and University of Central Florida has calculated what happens. So when we approach the tip here, close to the cluster, what happens is that if you approach the tip vertically without any voltage or the current, the top atom is getting loose. Here is show the energy barrier. This is the tip cluster distance, vertical distance. If you reduce the vertical distance approaching the tip to the cluster atom, the barrier for this top atom is dropping down drastically. At this point, the atom is very much free now when the tip is very close. And if you move the tip, the atom will follow the tip very easily. So you don't need actually much force to pull out the atoms. So we can produce the atoms simply by pulling out one at a time. So the question here is, what is the distance to approach the tip so that we can take out the atoms clearly? To find out, we do some statistical analysis. So here is the probability of atom extraction, and this is the current. So by changing the current in STM, we can change the height. So as you see here, the low current, that means a faraway tip, atoms cannot pull out. At a certain point, certain current, the atoms started to come out, so probability is becoming 1. Now, if we change the voltage at the different voltages, we have a different sets of currents. I will just quickly show the next slides. So these are how we measure. We have a different voltages, and we have a shift of the current at the different sets of currents. We call it different threshold currents. And if we plot it with this current and the voltage, threshold voltage and current, we get linear relationship. From the slope, we can measure the threshold resistance. And from that resistance, we can convert to the height by using the IZ spectroscopy. And we measure it here. Turns out that the tip atom, the apex atom, and the cluster atom has to be 0.6 angstrom or less if you want to pull out the atoms. How reliable this technique? I will show you here. We can pull out the atoms one at a time repeatedly from a cluster, as many as we wish. So, so all the presentation here on the structures that we built, all the atoms that we produce in this way locally. Now, before I move on, I want to explain another thing. When we move the atoms, this is how the atom sees on the surface. Here, the image is the individual atoms. This is a silver 111 surface, STM image, and it's shown in the 3 dimension. These are the atomic corrugation. And for example, if we have an atom here, if we want to move to the different location, this is how the atom sees. It's not the same as the movement. For example, the atom wants to move along this direction. This is the lowest diffusion barrier. It's easy to move. But if you want to move to the different surface directions, it's difficult for the atoms to move because there's a corrugation. So this is how the atoms move. So how do we find out? We record the manipulation signals. For example, the top signal shows how the atom jumps along these 110 directions with the single atom steps. When we change the tip direction to the 10 or 20 degrees, the atom cannot follow exactly. So the atom prefers to diffuse along 110 because of the lower diffusion barrier. But the tip is moving along other directions. So it moves like a zigzag, this kind of movement. Zigzag. This is, we can record it here in this manipulation signal. And in this case, the atom moves more smoothly. And this I'm going to show you with some movies, just to understand a little bit more. For example, So this is a movement along 20 degrees. So tip is moving along this. Atom prefers to move along this direction. It moves like a zigzag movement. Okay, and so if we listen this sound, I hope you will hear this sound. So there are breaks in between. That breaks is atom is jumping. Okay, so this is the atom movement along this direction. So in this case, the atoms move first two steps smoothly, and it goes along this. It goes along the different directions around these atoms and move again around these atoms. It moves smoothly so that the curve has a smooth curve and the sound is different. Let's see now we hear that sound. So this is the atom movement along the 30 degrees, okay? So we can actually generate this kind of sounds. In my lab, we have these generations, and when we move the atoms, the students are listening to the sound, so we know that atom is moving, it's along these directions, or which directions, roughly speaking, not exactly 100%, but this helps a lot of things. So this is an example of writing of Ohio University logo, which all the atoms here we produce locally by extracting as the techniques I show, and that's in a three-dimensional image how you see electronic waves between the O and the U. We call it this is a 2 quantum coral. There are 51 silver atoms to write this. It takes 26 hours. I show here as a very fast movie. Okay, and these are some of the images which we built, and this is one of the smallest smiley image. Right now it is in a high school textbook in New York. I have donated this one. And this is, my student was just making fun out of it. It's a mouth. But actually it's a two parabola to test the electronic structure of the local electronic structure. Okay, so now I will move on to the second part, which is now the molecules, molecular wires. And this is about the sexy phenyl, which is sexy phenyl is basically the 6 benzene ring connected like a chain. So we call it a sexy, which means 6 phenyl ring. In the STM images, the molecule appear like this kind of cigar-shaped device. Now we can play around all the manipulation techniques to study about these molecules. So first we did lateral manipulations. For the lateral manipulations, we have to approach the tip close to the molecule. We move it to the position to retract the tip. So we retake the image, so the molecule should be here. But many times we see occasionally molecule continues to travel itself without the tip. So we move it, release the tip, molecule just keep moving itself. So now it's very interesting story comes up. What's happening? Why this molecule is continue to travel without any specific guidance? And it turns out that the molecules are very sensitive to the local electronic structure, for example, defects and other standing waves. So the first question is, can we adjust the molecular direction, control at the atomic scale? To do that, we need to create a uniform electronic structure. So here what you see here is the individual atoms, single atom steps on the silver 111, and we have deposited the molecules which are sticking at the step edge here. And then we crash the tip at the here in this location. These are the debris. This is the crash site, so these are the materials produced from the tip crash. These are the 2 unknown sorbates. Most likely these are sulfur atoms on the silver 111. We use as a landmark. I'm going to zoom in into this area in the next slide. That's the landmark. And this is a cluster. And we are going to use the tip to pull out the atoms and build the structure here. So this is pulling out the atoms with the tip, and we built linear electronic structures. I will just repeat it again. So we pull out atoms from the cluster with the STM tip, individual atoms, and we build the structure. And then we put the 2 molecules at the one side, and the 2 atoms at the other side. Now we can move the molecule and release the tip. Molecule should continue to travel, this time atomically straight line, hit the target. So this is we use as an individual atoms target, single atom targets. And this, we call it a molecule gun. So this is the same one showing a different presentation. And to move the molecules along the target, and we shoot at the molecule in the next slides. The atom is gone, and this is bounced back here, and the molecule is changed the shape. The atom is incorporated into the molecule. This molecule is moved here for a comparison. So this is how the molecule take the atoms by bending the pi rings. This is, we can also shoot not necessarily at the lower part of the standing waves. We can also shoot on the higher part. For example, in this case, we shoot the molecules. I call it shooting because we move the tip, the molecule with the tip only a little and release the tip. It continues to travel itself. And it's going to hit here. So it just goes in a straight line, as you see. So important thing here is the uniform electronic structure to shoot the molecules, how it goes. Now it's interesting, physics is coming up, how these molecules are moving on the surface. So if we consider like a ball, rolling ball, so you roll the ball like this, continue with the momentum, it's a wrong physics because this is not classical mechanics. This regime is in quantum mechanics. So we want to know how the molecule is moving and what should be its speed of moving, for example. To do that, we must know, first of all, how the molecule absorbs on the surface. The problem is these molecules are physisorbed. So physisorb is basically like it's weakly bound on a substrate and it's easy to move. But if we want to get the atomic resolution on the surface, we have to approach the tip. We try to move it, then the molecule also moves away. So we don't get it molecule together with the atomic resolution. It's difficult to get it. So again, we use the atomic manipulations to position the atoms on the surface. Here, for example, we put the atoms exactly at the 6 atom distance apart. So we can now draw a net, and we know that the atoms are sitting at the 3-4 hollow sites. So we can draw this kind of net. From this, we can find out the substrate atoms, which should be in a crossing point of these lines. I draw it here. So this is a molecule. These are the marker atoms. We draw the net, and we see how the atoms are sitting. From this, now I can draw up the model, which is from measurement. It turns out that the carbon atoms here from the benzene rings are sitting as following. One side of the benzene ring, 2 carbon atoms are sitting on the top side of the substrate silver atom. The other 2 atoms are sitting at the bridge side. Now, if you carefully look at the molecule, you will see that they are slightly wiggle. I show this wiggle here with a line here. It appears as this kind of wiggle. And it turns out that the 2 atoms are sitting on top side. It appears kind of brighter. Okay, so there's some interesting thing there. Now, this is a close-up look. Again, it shows the single molecule, shows the wiggling. If that is the case, it's true, then if we move the molecules half of the atomic distance forward or backward, this case backward, it will switch. For example, the substrate has FCC and HCP sites. If we move this half the atom distance down, for example, then the bridge side will become the top side. The top side will become the bridge side. So the wiggle should change to the opposite wiggle. Okay. So the question is, we know that this molecule, the pi rings are twisted in the gas phase. Is it still twisted on the surface like this? But we don't know. So by luck, I'm sorry again, the image is cut off at the top here. By luck, we have this image at the before we have opposite wiggle. At the next scan, the molecule switch and appears at the same wiggle. So this proves that the molecules, by moving forward, can change the wiggle arrangement correctly. Second, we use the density functional theory to find out the corrugations. It turns out that the molecules, when we put the physics options, which is we calculated by fixing the distance 3 angstrom above, molecules appear wiggle, and they are, of course, slightly twisted, the pi ring. This is the calculated pi rings, and appears that this kind of wiggle is due to the twisting of the molecule, slightly twisted on the surface. So now we know that the molecules are twisted, and they are physisorbed. And we can also measure this vibration of this as a vibrational spectroscopy, second derivative signal, and appears at 186 millielectron volt. We have this signal appear. That is due to the twisting of the molecules. Now, in order to detect that how the molecule moves, we put the tip at the one side of the molecule, here at the edge, and we laterally move it. And it appears that every single atom distance, we see these signals, low, high, low, high. So what happened here is we detect low because the pi ring is down, because the tip is positioned at the edge of the pi ring, and when the pi ring is going up, the tip is moving up, and we see the high signal. So every single atom movement, this pi ring is moving like up and down like this. We are detecting low and high signals. So now we know that when the movement, pi rings are flipping back and forth. And luckily, we have this atomic corrugation is also matched with the substrate corrugation. So there is a theory proposed in 2000 by the Klafter group from Israel, from Weizmann Institute. They explain that if you have a single atom chain on a periodic atomic potential, if you move one atom to the next site, that translational movement, translational energy will be transformed as a potential energy, spring energy. That will bring the next atom and the next atom. So here, the movement is very simple. We have a transfer between kinetic and the potential energy back and forth. By doing that, we can move entire chain to the next site. In order to do that, we must have the isolated system. So in our case, what happened is that the molecule is a lattice match with the substrate, and it fizzes off at the liquid helium temperature. So we assume that this molecule's energy transfer is a bit slower, so it can maintain up to some distance, considered as a relatively isolated system. So this is our model, how the molecules are moving on the substrate after releasing the tip. So basically what we did is that the tip, we excited the torsional mode of the molecule, and when we release the tip, it just moves, it triggers the movement. Now, we can calculate the frequency of this movement because we know the energy, we measure it by the electronic structure. It turns out that the frequency equivalent to that energy is 0.9 to 10 to the power 14 hertz. One cycle of vibration is a 1 silver atom distance, as we know how they move. If we convert that to the speed of this, it turns out that 26 kilometers per second. If I compare with the fastest bullet speed, 1.3 kilometers per second. So this is, of course, in the nanoscale. This is in our scale. But this still is I would say this is still the fastest gun in the world at the atomic scale. Now the third topics, I will move on to the magnetic molecules. In this part, I'm going to talk about the Coulomb effect by using the molecules. So what is the Coulomb effect? If we have a free electrons scattered on a surface, and if we put a magnetic moment below a certain temperature, what happens is that the spin-electron interactions, exchange interactions, lead to, this is just a snapshot example, change the orientation of the spin. And that is known as the Coulomb effect. And by using the scanning tunneling microscope, with the single atom Coulomb effect was observed by two groups in 1998 by Mike Croming group from Berkeley and Schneider group from Lausanne. What they see here is that they have a single magnetic atoms, put it on the metallic substrate, which has a bunch of free electrons, take with the STM tip the spectra. Near the Fermi level, you see this kind of dip. And this is produced by the Coulomb effect. And half of the full width at half maximum can be converted to the temperatures known as the Coulomb temperature. And we measure this by using the funnel line shape. For example, in this case, when they measure on top of the atoms, you see the dip. But if you measure at the side, you see nothing. So in this case, this is the Coulomb effect. Similarly, in this case, selenium atom on silver 111. We also see the Coulomb effect. Now, we want to study this Coulomb effect on the molecules. So my group is one of the first group studying this together with other group from China. And because the molecule has a special interest, because we can make a self-assembly, we can create easy for nano devices by using the molecules. So we decided to study the Coulomb effect to look at the molecules. So we choose the porphyrin molecules with the center atom either cobalt or copper. Here, copper doesn't have magnetic effect in this molecule, but cobalt has a spin. So we should see the Coulomb effect here, not there. So we can also compare whether we see Coulomb or not. When we deposit these molecules on copper 111 substrate, we see this kind of structure. Two shapes. One is like a four lobes appear. I show with the drawing here. Another one is a two lobes. It's this drawing here. So this molecule can stay in a two different conformation, flat or bent. If you bend it, you see like a small appears two lobes like this. This one shows a cross section. This line is consider this as a substrate. You have then the flat molecule, cobalt atom is in contact with the substrate. Bent molecule, it's narrower because this is now reduced the distance, but the cobalt is lifted away, so that we have now a system where we have a two conformation. One, magnetic atom is in contact with the substrate, which has a bunch of free electrons. Another one, we can lift the magnetic atoms, so we can reduce the contact with the free electrons. Now we can play around to see how spin-electron interaction, which means the spin from the magnetic atoms and electrons from the substrate interact. And please remember that if we have two lobes, it's a bent, four lobes is a flat. Now the next step is whether we can change from one to another. So we start with a two lobes one here, a molecule, next to a copper cluster. We inject the tunneling electrons, and something happened. We inject it again, switch to the four lobes. So we can actually switch one molecule at a time from bent to flat by injecting the tunneling electrons. So we can manipulate single molecules, and we can switch it. And this is shown with the examples here. When we switch that, we can see two-step signals, which means it changes twice. Now the two lobes, which is a band, I show with a small dog here. There's a standing up. If you inject the electrons, half of them is flattened here. So the leg is here. Half is flattened. The other half is still bent. It's like this. If you inject it again, now it's completely flattened. You have now four lobes. Now we have a way to change the molecule, and we can change the cobalt atom distance away or close to the substrate. And then we measure the Kondo effect, and we see the Kondo effect. Remember, if you have a Kondo effect, it should appear, in this case, the dip, close to the Fermi level, which is a 0 volt in STM. And as you see here, this one shows a dip for the bent one. The flat one also shows a dip. Both are cobalt buffering. If we use a copper buffering, we see nothing. Here is copper. The same way for, this is called saddle, this is planar. In the copper, we see no signal because copper doesn't have any magnetic moment in this case. So we have now confirmed that this is the Kondo effect, and due to the spin-electron interactions. Interesting thing is, if you look the width of this is narrow and this is large. Larger width means the stronger interactions. Narrow width means weaker interactions. As expected, far away should have a weak interactions because the dz² orbital, which is one of the main contributor, is now far away from the substrate. In this case, it is in contact with the substrate. If we convert that to the temperature, we get it 130 Kelvin. This is the energy scale. You can convert that by kBTK. And this is a 170 Kelvin. So that higher temperature means stronger interactions. Now, where can we use this? This is the exciting part. We have now 1 nanometer size molecules, and we can change between this, at least from this to this in our case. So we can use this, for example, 0 and 1 signal. Then this will be a magnetic memory. So we can read and write. So the main interesting thing for us is, can we happen this in the two-dimensional assembly? So we move up the next step, that we start with forming the molecular layers. And it turns out that we can form this kind of ribbon-like structures forming the molecules. And if we look at the structures, it appears that the molecules are forming kind of a hexagonal arrangement here. Unfortunately, only the flat ones form this kind of hexagonal, while the bent ones are staying without forming in the structure here. Again, we measure the Kondo effect. We use both cobalt molecules, copper molecules. They both form, this is the cobalt, this is the copper molecules. Again, we measure the Kondo effect on one of the molecule at the layer. We see the Kondo effect in case of cobalt. We don't see anything here in case of copper molecules. We confirm that, okay, we have a Kondo. It's nothing new. But interesting thing is the Kondo temperature. I'm sorry, it's very sorry about this because something's wrong with my computer for the colors. It's just a red color, doesn't appear here. Appear here is a 120 Kelvin. 105 Kelvin here is. Now the question is, in case of the single molecule, we see 170 Kelvin. I just showed you higher Kondo temperature, but layer appears 105 Kelvin with the same structure. So what happened here? Why is that? Is it a spin lattice effect? So we have to find out about this. And when we deposit the molecules at the different temperatures, appears that the same molecules form two different types of structures. One is called parallel structures, not hexagonal. Another one is rotated the molecules at 120 degrees and forming a triangular arrangement and less ordered molecules in the clusters. When we measure with the spectroscopy on each one, both shows the Kondo effect and both have the temperatures close to 105 Kelvin, so that we know that there is no influence from the lattice arrangement, so we can forget about the two-dimensional Kondo lattice in our case, but it still shows similar temperatures. So in order to understand that, we have to find out. So what we did is that we create a small hexagon by removing the molecules from a ribbon with the STM tip. We have this kind of a hexagonal unit. I will just briefly show this movie again. So we move it with the STM tip, the molecules. We call it two-dimensional sculpturing. And we get this kind of a hexagonal unit forming the 7 molecules. Okay, so this is a ribbon. We created a hexagonal unit from the ribbon by tip. And so these are the 7 molecules. And we measure the Kondo temperature at the center molecule, appear the Kondo dip at the Fermi level. And we remove one molecule from the edge. We measure it again. We see the Kondo effect slightly wider now. And we keep doing that. We're measuring at the center. And each step, the Kondo signature is wider and wider. The width is. Okay. And now this is the library of how we did it. And this is how the signature is coming. And if we check this temperature by converting it, it turns out that when the molecules is surrounded with the 6 neighboring atoms, we have 105 Kelvin. By removing one atom at a time, it recovers to 170 Kelvin. It's quite good, so we are happy. Okay, so we have a connection between these two. But why this is happening? We can manipulate the Kondo temperature. We can actually tune the Kondo temperature between 105 and 170 Kelvin by removing this. Now we need to explain a little bit more physics. So it turns out that when we calculate the standing wave patterns, I explained before also in IJS logo and also with the other atomic manipulation, we have this kind of standing waves. Standing waves are produced by the free surface state electrons. It turns out that if we calculate, this is a calculated image. Another molecular clusters, there is no standing waves, but outside, yes. So the edge molecules scatter the electrons. So the center molecule should be around here. It doesn't have a contact with the standing wave, surface state electrons. By removing neighboring molecules, the center molecule is exposed to the surface state electrons and it starts to have a contact. On this substrate, we know that Kondo effect is contributed by substrate electrons as well as the bulk electrons, surface plus bulk. Here we simply remove the surface electrons. So it has only the bulk. In case of 7 molecules are surrounded. So now we know that this effect is due to the quenching of the Shockley surface states by putting the molecules around, and we can change the Kondo temperatures because we are manipulating the number of the substrate electrons to be interact with the cobalt atoms. Okay, so I will move on to my last part, which is the nanoscale biomolecules, a chlorophyll switch. This was quite popular. I will just skip this press. I'm sorry again. This actually, I will tell you now the colors. This should be a beautiful colors. Original image has a red, orange, and green. This is in the fall time, and we have a beautiful colors of the leaves. Also in Europe, especially in the North America, we have a very beautiful leaves colors. And this is due to the molecules. So this is called chlorophyll molecule. The chlorophyll molecule is you can find on the plant leaves, which produce a green color. This is absorption spectra of the chlorophyll molecule. as you see that the molecule absorbs all the color except the green color here. So when the sunlight falls onto the plant leaves, it absorbs the rest of the color. It doesn't absorb the greens, it throws back. So we see the green color of the plant leaves. But in the fall times, something happened in these molecules. Biologists said the molecule is dead. I don't know what does it mean. But something happened so that other pigments like carotenes, and they are also sugar and proteins, they produce orange and red colors. So this molecule is also important because this is a central role in the photosynthesis. That's the origin of life on Earth, because the plant leaves produce the oxygen that we breathe. And so it comes up that it would be nice to use the single atom manipulation techniques to study single molecules of chlorophyll. The idea started it because we wanted to study origin of life at the atomic level or molecular level. So let's start doing that. So one of my students was interested in it, so we started it. So this is the molecular structures. What you see in the plant leaves, the porphyrin has a head and a long chain carbon tail. Another interest is, of course, this is supported by Department of Energy in U.S., which is, it's again, the plant leaves are the best natural solar cells. It converts 95% efficiency solar energy to chemical energy that produce the oxygen. So if we have a way to use that and copy it for our solar cell process, we will have a cheap, environmental friendly energy converting devices. And so having these two ideas, we started studying this. So I used the spinach molecule produced from spinach, and we put it into our machines on a gold substrate. So this is how it looks like with gold 111 herringbone reconstructions. When we deposit the molecules, we see this kind of clusters forming well-ordered arrangement of the molecules. If we zoom in, we see like this. We have a round shape with unknown triangular shapes, very difficult to identify. So we have to first know the structure of the molecules. We calculate isolated molecules. So it turns out that chlorophyll stay like this. It's the porphyrin head. And then the tail is bent on top of the porphyrin ring. And this tail has 4 CH3 groups. It's like a bridge. Okay, 4 CH3 groups are supporting this carbon chain. And if you look from the top, you will see these carbon atoms 4, 5, 6, 8, 9, 10, 12, 13, 14 as higher. 7, 11, and 15 are lower because they are connected to the CH3 groups. So if you look from this, you will see these 3 triangles. I now label it here. This is the porphyrin ring. Here is the 4, 5, 6, the triangles. Okay, so this we are looking at the top. This is the tail. So this is the one molecule. That's another molecule, for example. That's how they are staying. If we look at the single molecule, instead of 3 triangles, we see only 3 lobes. That's the head. That's the tail. We start with a single molecule. I'm sorry again, my picture is cut off here. And we inject the tunneling electrons. We can change to these structures. And we inject the electrons again to the B, we can change to this structure. And we inject A again, we can change to these structures. So what's happening here is that we are changing the conformation of the molecule each time by using the 60-degree tail bending between each structures, between 1, 2, 3, and 4. And we can control it. For example, if we want to switch from 2 to 1, we inject only at the A. It goes between only 1 and 2, never change to 3. If we inject at the B position, it will change between 2 and 3, back and forth. Similarly, from here, we can inject in the A electrons. We inject at the A, we change to the 4. If we inject at the B, it will go back to 2. Now, I will explain more detail. So it's nice we can change the tail conformation of the chlorophyll single molecules in a controlled manner. Then what's happening here, we need to explain more detail. So if I explain that to the chemists, I said, with 60-degree changes, they said it's not enough. We need to explain more. So we, again, run the calculations. It turns out that if we want to change from A to B, it shows if we inject the electrons and if we rotate only one single bond called carbon atom 11-12 bond, and keeping the rest of the tail rigid like a tree, you rotate it, you get this structure. And if we rotate, see 7, 8 bond here, only the single bond, keep the rest rigid to counterclockwise direction, we get this structure. Similarly, if we rotate again this C1213 bond clockwise direction, we get this structure. So this is the library. What we are doing here is that we are actually rotating single carbon-carbon sigma bond at the two locations. One is a C1213 bond, another is C78 bond here. Each of the electrons, as soon as it switches, you see the changes. So this is the time, this is the current. So we can measure the rate of switching here. If we keep the tip longer time, we see this kind of digitized signal switching back and forth between these two. And we can change this frequency by increasing the current or reducing the current. So we can relatively control the frequency as well. We can also measure the energy of the switching by using the IV tunneling spectroscopy. As you see here, which ramp the voltage as a 0.8 volt, it starts to flip. And so we know that it requires the 800 millivolt energy. Okay, so now, if you want to rotate the carbon-carbon bond, chemist knows that you need a very small energy, not in a millivolt, it's in a microvolt range. So millielectron volt, why is that? Because this is on the surface. And what we did is now we use a fixed voltage and a current, and we switch many of them. For example, this data was collected over 100 switching events at the fixed current and the fixed voltage. For example, here about 70 molecules switch at this time, about 24 molecules switch at this time, and so on. It appears exponential decay in the curve, statistical analysis. From the exponential constant, we can calculate the time constant. And if we increase the current, we have another curve. Now at a different current, we have a different switching rates appear. I told you at the very beginning, please remember the equation which is explained as rate is proportional to the current to the power n. Now, if you plot a logarithmic plot with the rate and the current in a log graph, the slope would tell us number of electrons involved in the process. So here is a logarithmic plot. That's a rate. This is a current. Appears linear. The slope tells us 1. So we explain that we use single electron energy transfer to switch all the events here. We can also calculate or measure the statistical measurement of the yield, quantum yield, to switch, for example, in this case, 2 to 1 and 2 to 3, switching for the quantum yields. So how do we use that? In US, we need to explain everything to get the grant funding. So I said, well, we can use this nano-selector switch or multiple logic. And this is quite famous because now the people in India think that they're eating spinach, the vegetarians. Now they can connect the spinach and nanotechnology. So this was also in a Paris fashion show, how we switch the single molecule of chlorophyll. These are the animation of different STM images. Okay, so to conclude my talk, I start talking with the extraction of the individual atoms for manipulation, and I explain about the single molecule gun, and I talk about the Kondo switch. Finally, I talk about the spinner switch, and thank you for your attention. And this is my group with some music. You don't hear much. Okay, so these are my grad students, Violetta. She was the one who measured the chlorophyll, and she is Aparna. She is the one who make all the manipulations mainly. And Joe Vaughn, Kenneth Clark is now working on the biomolecules. Thivo, who was involved in building the machine. Kiani, she is working on Kondo effect, work on semiconductors. Thank you for your attention.
Thank you for this really spectacular talk. I'm sure we have some questions from the audience. Igor, please.
Also, I have a spinach question. So how do you really put spinach in your STM?
All right, so the molecule is produced from the spinach. It's 99.999% purity. Oh, 97% purity, sorry. We bought it. Yes, from Sigma Aldrich, yes. It took us almost a year to learn how to deposit these molecules. Of course, my students work for that. So just give them, encourage them. And because the the chlorophyll is liquid, almost liquid at the room temperature. And it's also very sensitive. We have to order it. As soon as it's ready, we have to deposit. It comes with the ice pack. Basically, it's freeze.
It decomposes at high temperatures or what?
Yeah, we use at about 200 degrees Celsius source temperatures. And these molecules are very strong. You have to remember that the people confuse about this. So the carotene, we also work with carotene from carrot and chlorophyll. So I found out that the molecules that we synthesize are weaker. And these molecules are extremely strong. If you try to crash with the tip, you cannot easily destroy. You destroy the tip, not the molecule. Because they are carbon-carbon bond, carbon is very strong. The tip is metallic, in this case, coated with silver, because we crash the tip. And if you don't put water, then these molecules survive very, very strong. That's why they are naturally selected over billions of years. Thank you.
Especially parts, you showed the manipulation of the molecules, the beloved. Now, the question is, when you trigger, you can actually start the self-assembly process when you trigger, for instance, the 3 solo atoms or manipulate a couple of molecules. Now, the question is, how large structures you can really sample in this, considering the energy and time scale.
Okay. So manipulation technique is not engineering technique to assemble for production technique. Yes. So it really takes time, especially if you want to have beautiful images. So we move, take the image, take the image. It really takes time. So what we do here is that, of course, we can isolate and we can study about these molecules and how it works. So it takes time. Yes, it takes. So in case of for example, to remove the molecules to form the hexagonal structure, it takes about 6 hours. Switching here doesn't take time because it's in a few seconds. Because the switching here we can detect in a milliseconds. Actual rate is of course in nanoseconds or picoseconds. Oh, thanks.
I was just wondering quickly, could you please repeat how does this molecular diagram really work?
Okay.
What does it actually carry the molecule once it's ready?
Okay. It's a very good question. Actually, I actually want you to get it because that's the key.
I hope you don't have any need for it.
Well, we cannot shoot to Iraq because it's too small, right? So, well, I was actually trying to get the DoD grant without success. Okay. So, all right. So how it works is, okay, that's a molecule. The molecule, first thing, they freeze up, okay? Second, they are slightly twisted. I'm sorry about the laser lighter. Second, they are slightly twisted. In the gas phase, they are twisted about 40 degrees. We also measure it by STM. We have 11 degree twisted still. Now, the molecule is exactly lattice matched with the substrate along this direction, only in this direction, okay? So what we did is that we go in with the tip, we distort the molecule, drag it a little bit, and release it. At that moment, when we distort with the tip, we are actually conforming this twisting mode. We excite it mechanically. When we release it, it just excites like this. Now, under the tip, the potential is slightly lower than the other side. So molecule has a tendency to move towards the tip and move forward instead of backward. So it's like you have to see like a pinion and a rack. So this movement, if you excite it, because this is matched with, is grabbing, moving like this, it's matched with the lattice, so it's just keep moving.
Would be something like the Brownian motor that
Brownian is a little different. Brownian motion has temperatures involved. So here we do not consider the temperature is involved. Temperature means the photons, substrate lattice vibrations. But the molecule if you consider molecule as a Brownian, maybe yes.
I'm guessing that there is faint chance that actually once you excite a molecule to go to the left, once out of 1,000 it may actually end up going to the right.
In principle, it should not have any distinction between left and right because the molecule and the substrate doesn't have any directions.
I mean the side opposite of the
Right. But the only reason it's moving forward is because of the potential energy is lower under the tip because of the tip.
Oh, so it always ends up.
Yes, yes. Because of presence of the tip. Suppose that if you excite this with a laser light, okay, without the tip, then the molecule should move in the both direction, left or right. It should not have no memory or left or right. Now it has a memory because of the tip.
How energy is dissipated in this process?
That's a very good question. We wanted to find out. So what we did was, okay, it should stop at one point, right? So we can calculate. But it turns out that we cannot find a stopping point. It always go and stick into somewhere else. So because the surface, the best prepare is free of the defects. The best is about 30 nanometers, about 300 angstrom, the best clean area. And that molecule easily goes.
It's almost kind of a ballistic type of movement.
Yes, ballistic type of movement.
Any other questions? If not, let's thank the speaker again.
Okay, thank you.
And before you